Wait, yes, now it is recording. Okay, so welcome everyone to this third session of our weekly meeting on quantum information. And so today we are going to listen to Sahil Naik, who will be presenting the second part of the process matrix formalism discussion, which started last week. Okay, so let's start. Sahil,
Yeah,
over to you.
okay. Yeah, thank you. So this time I'll be discussing a paper which appeared in archive quite recently in on 20th March this year. So the name of the paper is Cyrilson Bounds for Quantum Correlations with Indefinite Causal Order. Okay, so I'll explain what is the title in some time, but before that, let me just give a quick review of what we discussed last time, and then I will go to this paper. So, last time, what we saw is that suppose we are in such a scenario where we have some parties. So, last time we discussed it just for two parties, but you can generalize the thing for as many parties as you want. So, let's say I have lots of parties and each of them performs some local experiment in their lab. So here we denote the local experiments by some most general operation which we call a quantum instrument. So let's say I denote the instruments of Alice by this index, where denotes the outcome of her instrument and X denotes which instrument she is applying. And similarly for Bob, you have the CP maps of this form, and so on and so forth. So the constraint that these maps have is that if you take these CP maps and sum over all the outcomes, this should be a trace preserving map, or we also call a channel, completely positive trace preserving, or also known as channel, a quantum channel. So similarly, you have the same constraints for Bob. So this has to be true for all the instruments that Alice chooses. Similarly for Bob. Yeah. And so on and so forth for all the parties. Now, the question we asked last time was what are the sorts of correlations that Alice and Bob can generate if you assume some particular thing about their local laboratories. So if I look into, let's say, Alice's local laboratory, the assumption that went into this was that there is some quantum system which enters her lab. She performs some based on some freely chosen variable x. She performs some instrument given by these CP maps, and the updated state, which we denote by the Hilbert space A0, and similarly the input Hilbert space is AI. So the updated state is sent outside her lab, and she gets a classical outcome A out of it. So this was the assumption. So which we also said it is the single opening setup. Yeah. So we have these assumptions for all the parties, and particularly for two parties, we saw that the set of correlations which they can generate in this particular way comes from the object, what we call as a process matrix. So as I explained last time, the process matrix is basically a positive operator in the four-party Hilbert space. So let me write it in shorthand. The four-party Hilbert space. So this is some operator in the that Hilbert space which is positive, and also this W belongs to some particular subspace in that in the operator space. So it's a positive operator in the operator space, and it belongs to a particular subspace, which is coming from basically the trace preserving condition. So what we see is that the correlations that we get, so particularly for two-party case, so the correlations that you get can be written in this form, and which we saw as the generalized bond rule, which is basically a bond rule over the process matrices, over the process matrix on, yeah. So where these are nothing but the CJ operators of the corresponding instruments, the corresponding CP maps of Alice and Bob. And here also this process matrix is essentially the CJ operator of the abstract transformation W. Yeah. So this is what we discussed last time. So as we saw that in general, the correlations that you get here, so these statistics are known as correlations. So in general, the correlations that you get here will be signaling, as opposed to the usual no signaling correlations that we see in Bell scenario. So, and what we, apart from this, what we saw is that uh, there are some processes which we cannot write as convex mixture of separable processes in this form. So this is the no signaling process. So this is the process where Alice cannot signal to Bob, and here Bob cannot signal to Alice. So there are some processes which cannot be written in this form, and some of these processes we argued that they are able to violate what is known as causal inequalities. So now a natural question that what one can ask is that what are the optimal violations of this causal inequalities? As in, how far away from the uh, causal setup can we actually go using these processes, these quantum processes and the instruments? So this is the question that is asked in this paper, and they are particularly trying to answer this question. So let me give a brief review of what is where the term Tyrellson comes from. So for that, let's go back to the usual Bell scenario. So uh, so this is a different setup. This is not the setup that we are looking so far. So this is the a setup where you have two parties, two or more parties who are space-like separated. So here actually we assume a particular causal background where the all the parties are space-like separated to each other. And let's say we look at the very simplest case where all parties have binary input and output. So, and here one can define the BCHSH operator. Okay. And you can show that the expectation value of the operator is always bounded by 2 for any theory which has a local hidden variable model. So under this assumption, Bell derived this inequality. And what one can show is that if you use quantum mechanics, as in if you look at quantum correlations that you get in this scenario. So now what do I mean by quantum correlations? So I say a correlation is quantum. So I denote it by super index Q. If I can achieve it by some density operator and some POVM measurements on both the sides. So call it a quantum correlation in this case. So one can ask that, so what one finds is that you are actually able to violate this inequality. And for some particular quantum correlation, one can show that you can actually get more than 2. So it is impossible to give a local hidden variable kind of explanation for quantum mechanics. So, so what do I mean by local hidden variable? Here, there are these assumptions, which is the realism assumption and locality assumption. So these two cannot simultaneously hold for quantum mechanics. So if that is the case, then Cyrusson was the first who asked this question. Who answered this question? That what is the optimal violation that one can get here? And as we all know, the bound is, so he derived this bound. The optimal quantum violation is 2 root 2. Right? So similar to this spirit, the question
Sahil,
this yes, yes.
Sahil, here I have some naive query. To find the optimal value, I think we can take projective measurement instead of POVM because since there is no dimension restrictions, right?
Yes, yes,
Okay.
yes. So I'll come to that. So
Okay.
I'll tell all those things because that is needed for this discussion. I will tell all that in some time. So you can restrict to projective measurement and pure state and all these things. Okay. So yeah, as I was saying, so this was the bound that Sahelson has derived, and you cannot get more violation than this for using quantum theory. So this exact parallel question one can ask for the previous thing that I discussed, as in if I have some causal inequalities, then what is the optimal quantum violation? Okay. So what do I mean by optimal quantum violation? So I should be able to get that violation by some quantum process and local instruments of Alice and Bob. And so other parties, if there are more than 2 parties. So first thing what we can do is let's look at the particular causal inequality that we discussed last time. So I'll discuss 2 of these inequalities. One is the guess your neighbor input.
Sahil, I think Kanjilalda has some questions. So I'm saying if anyone want to ask some questions, he can directly unmute himself and ask the questions.
Yes, yes, yes.
Okay.
What is the
Okay. So I have a question about the earlier session. So when you wrote the generalized Born rule for the channel, you assume that you have CJ isomorphism, like you
yes,
assume some kind of CJ isomorphism kind of structure, right? So
yes,
now CJ isomorphism, posits a kind of maximally entangled state. right?
Yes.
So now the whole thing. So your can we from there can you argue that okay, whatever that when you get the so if the theory does not have a CJ isomorphism kind of thing, you cannot write the write the process matrix formalism or maximally entangled state per se.
Means if the
Then
theory does not have a maximally entangled state, so what is
yeah.
the
So in that case, can you have a process matrix formalism or some kind of generalization of the
okay?
you know
So I understand. So CJ isomorphism is just a tool to convert abstract maps to operators because we know how to do the calculations for operators, right?
Mhm.
So we know how to do the calculation for operators, right?
Yes, yes.
So that's why. So this is just a tool to convert all the maps, etc., that you have in your theory to operators. Now, if you have linear maps in your theory,
Mhm.
so which I suppose you always assume because the map should preserve linearity, as in the convex mixture of two different states. The output
Yeah,
of the map should be the same as the output of the convex mixture of the outputs of the two states. Like
yeah, yeah, yeah,
that
yeah.
is a very
Yeah,
natural
linearity
demand.
for convex. Yeah, yeah.
Yes. So as long as we have this linear structure, what we can do is we can always denote these objects, these maps in using some operators in
Yeah.
some this thing. So like means particularly whether we can use CJ isomorphism or not, I don't know because especially depends on the
Okay, but you
this
say that
existence
there
of
would be an
maximal.
isomer. Okay, I understood. You say that there would be an
Yeah.
equivalent kind of isomorphism between the linear maps and the operators, right? It may not have.
Yes. Yes. Yes.
Okay,
Yes.
okay,
So
okay.
so as long as that is there, then we can always come up with some process
Ah,
metrics framework for that theory.
okay, okay, okay. Thanks,
Yeah.
thanks.
So especially maximally entangled state kind of thing is not needed.
Yeah,
Yeah.
yeah, yeah, yeah. Okay, okay. Thanks a lot.
Yeah. So as I was saying, so last time I discussed this particular causal inequality, which we call guess your neighbor's input. So it's very straightforward. What is the task? You have an input for. So this was a bipartite causal inequality. Since there are only two parties involved, so you have two players. They have some coin states as their inputs, and they have to guess each other's input. Very simple. So b is equal to x. So these are the winning conditions: a equal to y and b equal to x. So what we saw is that the success probability for any separable process will always be bounded by half, but in general, for some arbitrary indefinite causal order process, it might violate this bound. So the question we are trying to ask here is, can we give a upper bound for this or a optimal violation to find out what is the uh, best success we can achieve in this kind of games? So that is one particular inequality. One more inequality I want to discuss. This is called the lazy GUI game. So what is this? It is a same game, but there is some relaxation to it. So what is the relaxation? Very simple. So Alice's guess should match with Bob's input if her her own coin state is say 0. And what about the case when her coin state is 1? In that case, we don't care what is her guess. It might match with Bob's coin state or it might not. And similarly, Bob's state should match with Alice's input if his coin state is 0. Okay, so in some sense you can understand why this name is given. So this is a lazier version of the task, so they don't have to always guess each other's inputs. They have to guess only when their inputs are 0. So that's why this is named lazy GYNM. Okay, so there is a difference between these two kind of games, so that we will see. So what is the paper trying to tell us? So they say that for such kind of games, so I'll give the explicit difference. What is the explicit difference between these two games? So for such kind of games, which they call this kind of games, you can always find the optimal bound. But here we can not find the optimal which is achievable, but at least we can give a upper bound in these cases. We can derive a upper bound on the optimal violation of any causal inequality. So how to do that? So first thing is, let's try to write down the most general causal inequality. So if you have, let's say, some players now, I'm trying to write it for, oh, sorry. So let's say you have Alice 1, Alice 2, and so on and so forth. So I'll denote the output by this vector, the string of the outputs. And similarly, the string of the inputs is denoted by this. So here you will generate some correlation in the process matrix framework. And a causal inequality is basically, you can write it in this form. So they denote causal inequality by this index I, which is basically some payoff for each input and output. So like you can, for every string A and X, you can assign a particular payoff, which I denote by alpha of A given X. And you have this payoff for all possible strings A and X. And this is what they call a general causal inequality. So the one which we saw last time, that particular payoff function was the probability of success of guessing each other's input correctly. So that was a particular kind of payoff, but in general, you can have some arbitrary payoff. Okay. So what they argue is that in general, for any causal inequality, I can always take these payoffs to be positive, some positive real numbers. Okay, so that proof I am not going into, but it can be argued that whatever causal inequality you come up with, there is some equivalent causal inequality which has the same form, but with some positive payoffs. So that one can always do. Now, yeah, yes. So as I was saying, so what we want to do is we want to give this optimal bound, but there is some difference kind of causal inequalities. As I mentioned, there are some ones for which we can find the exact bound, and for the ones for which we can give for which we can only give an upper bound. So these special class, like the lazy GYNI, these they call as single trigger causal inequalities. So what is the meaning of a single trigger causal inequality? It's very simple. So we say that uh, any causal inequality can be determined by the payoffs, right? the collection of the payoff. So we say that this is a single trigger causal inequality if the payoff of has this form, as in it depends on AI. So AI is the outcome of the ith party. This payoff depends on AI if and only if xi is some particular value zeta I. As in, for a particular value of xi, that is zeta I, this payoff is allowed to be a function of the output of that party. So now you can see, you can relate that why this lazy GYN falls into this category, because here the payoff that we are giving is only for each party. The payoff is there only if a particular question is asked to them. As in, for in this case, the zeta I values are 0 for both the parties. So that's why this falls in this category, which is called single trigger causal inequality. So for these kind of cases, we can derive an exact achievable bound. Okay. So not only that, what is important is that in this paper, they have said that for single trigger causal inequalities, they also tell you how to achieve the bound. They give you an explicit protocol, as in they give you an explicit process and the choice of instruments for all the parties to achieve this particular bound. Only for the single trigger case, not in general. Okay. So how to do that? So to discuss, to do that, first I need to discuss some things related to what Mirza was saying. So as he pointed out, they in the Bell scenario, from the Normark dilation theorem, we can show that any quantum correlation, the general definition of quantum correlation is this: some quantum state, some density operator in the bipartite Hilbert space, and local POVMs of Alice and Bob. This is the general definition of quantum correlation. But from the dilation theorem, you can say that if a correlation is quantum, you can also achieve the same correlation by some pure state, possibly in higher dimension, A prime, B prime, and some projective measurements on Alice and Bob system, as Mirza pointed out. So any quantum correlation, I can always achieve it by pure bipartite state and projective measurements. So what does this do? This reduces our search, right? Because earlier we had to search to find the optimal for a particular Bell inequality. We had to search over all density operators and all POVMs. Here we have to search only on pure states and projective measurements. So they ask what is the equivalent thing we can do here in this process matrix framework. Okay. So they, to do this, they say that they define the concept of what is called a projective instrument. I'll tell what is that. So instrument, yeah. So what is a projective instrument? So it is a map of this form. So the outcomes of the map A So when this map acts on some state, it takes this form. Okay. So as you can see, I can only define projective instruments only if the input and output Hilbert spaces have equal dimension. So essentially what this is doing is, so this is an instrument which does the projective measurement on your input quantum state. And the outcome of the projective measurement is given to you as the classical outcome, and the evolved state is given by this state, PA rho PM. Okay, so such an instrument is called projective instrument. And then they also define something called as labeled projective instrument. Okay. So what is a labeled projective instrument? So suppose I have lots of instruments of Alice. Okay, so let's say I denote the instrument number by X, and I will call it a labeled projective instrument if it is of this form. It acts on the state row in this fashion and also gives you a classical state as output, which is nothing but, oh, I'm sorry, it shouldn't be this. So, so along with the evolved state as in before, it is also giving you object rho x such that rho x um, trace of rho x prime is equal to 0 if not equal to x prime. So basically what it is doing is, it is essentially the same thing as before, but it is also generating a state rho x, and these states are orthogonal to each other for different values of x. So looking into this particular state, you could say in principle which instrument was performed. So that's why it's called labeled projective instrument. So this is essentially the label part. Okay. So this is where the first theorem comes in. So I'll not go to the proofs of the theorem, but so what they are saying is, if you have some instruments of each party, so let's denote for the ith party, let's denote the instrument in this form. Okay, so these can be any random instrument. And let's say you get a correlation out of it using some process matrix S. So they are using this symbol, that's why I'm using S. So S is a process matrix. So actually, so what you have is a correlation of this form, which can be written as trace of M A1 given X1 tensor. Like if there are n party. So what the theorem is saying is that if you have local instruments for each party coming and some process matrix, then the correlations that you achieve from this can also be achieved from other process matrix and labeled projective instruments. So I can also achieve the same correlation from some other S prime process and some M prime, where all these are labeled projective instruments. So you can see the parallel between this and the Neumark dilation theorem. So there what we did was essentially the POVMs, we converted it to always projective measurements. Here, what we are doing for every choice of local instruments of Alice, Bob, and all the parties, you can always get the same statistics from labeled projective instruments and some other process matrix S prime. So that is the theorem. So now, as you
Sahil,
can see, yes, Mida.
so you see, the earlier cases when you wrote your process matrix was you wrote process matrix as well as your instrument in CJ isomorphism format, right?
Yes.
But now your aim
Oh,
right now, your aim is not a CJ format, right?
yeah, sorry. So I'm sorry for that. So maybe uh, I'm using the same symbol. Yeah. So I mean actually the CJ here.
Okay.
Like,
Yes.
so
But then for the
so just
instrument,
a second. So
okay, okay.
here J are some arbitrary CJs of instruments, and J primes are CJs of local of labeled projective instruments. The prime versions are CJs of the labeled projective instruments. Yeah. So is that clear?
Fine, perfect. Thank you.
Okay.
Are there any,
So
hi Sahil, I have a question.
yes.
Are there any other conditions on S prime? For example, in the earlier in the quantum state case, it was changed from mixed to pure. So there is.
Right. Yeah. So like in their theorem, they have not said anything because probably because for their proof they don't need any condition. Okay.
Thank you.
But yeah, but in general, this S prime will be some other process matrix. Okay. In
Right.
higher dimensions. Okay.
Right.
Like, but they have not made any comment on the S prime part for this particular theorem. Okay.
But do you think this S prime will sitting in the extreme point of the process matrix? I mean, the process convex set.
Uh, that I don't know. Like means
Okay, I
I
see.
was
I see.
also thinking that means the immediate generalization of that is this. So
I see.
probably yeah, what you are saying probably is correct, but means I cannot tell. Like we have to see the calculation properly to understand this. Means
Okay, perfect. Thank you.
okay.
Sahil, just one small curiosity that when you write the labeled projective instrument, go a little bit up.
Yes.
Yeah. You get this also the label system, which
Hmm.
is kind of constant for all possible row, right?
Yeah.
Which does not
Means
vary here.
it's like means it's like if I do the first instrument, it is let's say giving you cat 1 state. If I do the second instrument, it is giving you cat 2 state. In that,
Okay.
it's like
So
that.
it does not depend on the row. So whatever row
Exactly.
you are actually
It does not depend. You're right.
okay. So when you
It
write
only
the
depends on X.
CJ, so what will happen to this part? This acting on the row part is fine. So you can act it on a part of a maximally entangled state. And what will happen to the other system? It will just be there, like for tensor.
Acha. That is your question. Okay. So, okay, let's just see what happens. Uh, so I need to send, so let's say this is from AI. So I need to just send this 5 plus in
Mm-hmm.
AI and
Mm-hmm.
act identity tensor in a given X, right? So this is a linear operator, right? So for every row, I get this particular thing. So whatever ma given x, even if it acts on some arbitrary operator beta, the action is something like this, right? Beta need not be positive operator like this. So basically what will happen is this, I can expand like this, sum over ij. So this will give me tensor PA ij PA tensor rho x, like that. You understand? So
Okay.
you'll just get some constant outside. That's all. Some constant density operator outside. Yeah.
Okay. Okay.
Yeah.
So
Like
so that is a operator which will be there for always. Like even when you write the bond rule, it will be there.
yes, yes, it will be
But
there. It will be there because it is a part of the CJ, right? Like
yes,
it will
so
be there.
then on
So
the process matrix part, it will be S prime tensor identity on the row X part, right? I mean, whatever that
no, no,
system
no,
is
no.
based on.
I don't. So that's the point. So okay, I understand. So here I see. So I understand your point. So here, what is happening here? This MA is a map from AI to sorry AO, the linear
Right.
operators of AI to AO. So this object is a map from AI to L of AO tensor some auxiliary system, where the auxiliary system is the label basically,
Right.
right? So now my S prime will be some process whose input is AI and output is AO tensor A auxiliary.
Okay. So that tensor, like the process matrix, will have the support on the whole thing. Like I mean,
Exactly. It
AI.
will, in general, it might have support on that. Yes.
Okay. Okay.
Yeah.
Okay.
Yes. So, okay. But the point is, it will still be a valid process matrix, whatever that object is in that extended Hilbert space. It will still be a process matrix.
Great. Great. Okay.
Okay. So, yeah, as I was saying, you can always, any quantum statistics that you get here, you can always get it from labeled projective instruments. Now they define something called as the canonical instrument, which will actually help them to give the bound. Okay. So, like, how much time do I have? Oh, I don't have a lot of time. Okay.
You have around 15 minutes.
All
So
right.
if we
Okay.
started a little, I guess everyone will understand.
Okay. Okay. So, so you see here, labeled projective instruments are of some particular form, but a canonical instrument is something which has even more structure than labeled projective instrument. So what is that? So a canonical instrument is basically, it is of this kind. So it is defined over the these kind of objects. So you have to take the, so when I define an instrument, it can be in any dimension, right? So a canonical instrument is defined in a particular fashion. It has to be in a particular dimension. So the input dimension you take as the number of settings of Alice. So this, sorry, the number of outcomes. So m of Alice. So these are the number of outcomes. So the number of outcomes are defined according to the scenario that we are interested in. For example, in the Jiva and I case, the number of outcomes of Alice were 2. So in this particular case, to define the canonical instrument, I will take the input dimension of Alice as 2. And the so basically here my the Hilbert space for AI will be nothing but CMA, where MA is the dimension or the number of outputs of Alice. And you define the output Hilbert space as same as the input space, but you have to tensor it with some other auxiliary space, where the auxiliary space is the dimension of the auxiliary space is same as the number of inputs of Alice. So this NA is the number of inputs of Alice. So for the GYNI case, even this number is also 2. So if you go into the GYNI scenario where each party has 2 inputs and 2 outputs, for defining a canonical instrument, I will take the input Hilbert space as 2-dimensional and the output Hilbert space as 4-dimensional. Okay, that is clear. Now, here you define this canonical instrument in this fashion. So why are we doing this? Because let's try to remember, because we want to give the optimal for single trigger causal inequalities, right? So I am telling you how to do that. Causal inequalities. So let's say I have all these parties A1 to AN. I denote their outcomes by A and their inputs by X. And let's say I am interested in a particular single trigger causal inequality. So if I'm interested in a single trigger causal inequality, I have to tell you what is the trigger for each party. So I have to tell you when does their output is dependent on the payoff. So for each party, I have to define a zeta. So I have to define zeta 1, zeta 2 for all the parties. So essentially, I'm defining some vector zeta. Okay. So which is basically element of all the possible vectors x. So zeta is a particular vector which defines the trigger for each of the parties. So now the canonical instrument is of this form. So it is basically, so I'm defining for the ith party what is the instrument. So ith party ai given xi. So it is of this form. Okay. Where, so you see here, the canonical instrument is a labeled projective instrument. So it's a labeled instrument, first of all, and there is something special about the label. So these labels are orthogonal vectors. So you get some orthogonal pure vectors as the output of the instrument, which tells you which instrument was performed. And this particular object is, when it acts on rho, it acts in this way. It does a particular projective measurement, and it is a rank 1 projective measurement, and the outcome of the projective measurement is denoted by this AI, which is basically the output of the party. Okay. So this N acts in this way only if the input is the trigger. Okay. So this MI is a labeled projective instrument for the case when xi is the trigger zeta I. Okay. And what happens when it is not the trigger? So when it is not the trigger, it acts in this way. So short way of saying is this is that it doesn't do anything on the state basically. So when you send in a state row, it sends the same state outside with some one by with equal probability. It gives you all the random outputs. Okay, you remember what was this mi? So mi is the number of outcomes of the ith party. This is number of outcomes of ith party. So basically here what we are saying is if it is a trigger, you do this projective measurement and give the updated state as the projector. And also you give the label with it. And if it is not a trigger, then basically what you do is you send the same state outside without doing anything and randomly produce one of the possible outputs. Okay, with equal probability. That's what this particular canonical instrument means. So now what you can do is that if you look at this causal inequality, which I wrote earlier, which we can write in this form. So here, if this is coming from a valid process matrix, I can just write it as something like this. S is the process matrix here. Okay, I should write J A1 X1. So dot, dot, dot. Okay. Now I can take the summations inside and basically write it as trace over S and some quantity mi. So what is this mi? Mi is a operator given by this. Okay. So you essentially take the summation inside over all the instruments, and you can basically say that okay, I want to now optimize the instruments present inside here and as well as the process here. Okay, fine. Now, like I think I'm about to come to the end of this, so I will tell the result quickly. Okay.
Sahil,
Yes.
you see this J, this individual J are some positive operator, right?
Right.
But this capital Mi, what you have written finally,
Hmm.
this need not to be a positive operator, right?
It will be
Because of
positive
L.
operator. Yeah, it will
It
no,
will be
but it will
positive
be
because L
positive
is a
because
positive. L is positive. LAX is positive. That's why.
yeah, no, this is not L. Like this is alpha. Okay, alpha
Oh,
AX.
I got
So
it.
as I said, for every causal inequality, alpha can always be taken as positive. So this mi is some positive operator.
Good enough.
Okay. So now here comes the highlight of this paper. So what they are saying is that okay, let's fix our instruments. Okay. So let's say I fixed to some particular set of instruments. So that means I have fixed my mi. That is clear, right? If I fix all the instruments of all the parties, then my mi is fixed. Now we are basically asking, I want to find what is the maximum value of this over this. So this will tell me what is the optimal violation of this causal inequality if you fix the instruments to these particular values, right? Now you have to optimize over all the process matrices here. Okay. So now what they have shown is that if you restrict to the single trigger case, okay. So if I restrict to single trigger case, okay. So this theorem is for single trigger case. So let me write down the theorem. Yeah. So what they are saying is that suppose you have a mi which is coming from some choice of local instruments. Okay. Now they are saying if you are in the single trigger setting, then I can always decompose this mi as convex mixtures of some other mijs where mij are canonical instruments. So is the theorem statement clear? Hello. So yeah.
Yes,
Yes,
yes.
you
So
can go ahead. As questions
yeah.
they can
So
ask. So
yeah. So in the special case when you have single trigger, so single trigger means my alpha are of particular form. They are of single trigger form. They cannot be arbitrary payoffs. Okay. So this mi also depends on this alpha, right? So in this special case, I can always decompose this mi as convex mixture of other mijs, where each of the mij is a canonical instrument. Okay. So what does this tell us? That it tells us that if I want to optimize a single trigger causal inequality, okay, so I of a single trigger, I can be guaranteed that the optimum will come from a canonical instrument. Since if you assume that it is not a canonical instrument, all parties are doing some arbitrary instrument. In the single trigger case, I can always write it as convex mixtures of canonical instruments. So the optimal must be coming from some one of the particular canonical instrument at least. So this is how they give you the bound. Now, what they can do is they have defined the canonical instrument here, right? This one. So this is a explicit instrument that they have defined. They have defined a particular kind of instrument. So it tells you exactly what it does when you have a particular input, what output it gives. So this you have essentially fixed your instruments to this form. Now it is very easy to see that the optimal value of this single trigger uh, will just be trace over S mi canonical max over S. Yeah. Now this they say is a very efficient problem. This is a SDP problem. Okay, because you have essentially fixed your instrument. You only have to optimize over your process matrix. So this value you can exactly find. So from here, they have actually given you a protocol to find the optimal value as well as how to achieve that optimal using this SDP. So how to achieve it? You use these canonical instruments for each party and you do this SDP. You will find the optimal process matrix which gives you this optimal value. So that is the main point. Okay. So for a particular class of causal inequalities, which are the single trigger causal inequalities, they have told you how to actually achieve the optimal bound. Okay. So let's look at the particular case, lazy GY Naik case, as I was saying. So this is a particular causal inequality. If you find the optimal value, it will turn out to be, just a second, let me check once and yeah, this will be 0.8194. And actually, what the other people, so there was a paper by Cyril Bransiard. So there they did this seesaw algorithm for this lazy GYN case, and they were able to achieve this in that uh, particular paper. And from this paper also they are matching it that actually this is the bound. So also one more thing they did. So the optimal that they were getting in that paper, the Bansiart paper, that was coming from qubit processes, and this is also giving you essentially the dimension the dimension to should be C2 for every Hilbert space. That is coming basically from the canonical instrument case. Means the output should be C4, but the input should be C2. Yeah. So that is what they have found. So what is the interesting lesson to learn here? That we cannot win the lazy GYNI game perfectly. Now, the power here is that the power of this result is that usually when we ask the optimal for any particular thing, any particular inequality, causal inequality, we don't even know what is the dimension of the objects that I should be working with, like what dimensional object process metrics I have to take, what are the dimension of the instruments, that I don't know. But here for the single trigger case, they are telling you that you will get the optimal in this particular dimension. It might happen you might get the optimal in less than this dimension, but they give you explicit protocol of how to get the optimal. Now this is the last thing, so I'll just take 5 more minutes. So what about the other causal inequalities which are of not this form? So as we saw clearly that there are some causal inequalities like this one. So this is clearly not a single trigger causal inequality, the GY1, because here your payoff doesn't depend on a single trigger. Your payoff is dependent on all the questions, right? Whatever input you are getting, you should always be able to guess the other party's coin shit. So this is clearly not a single trigger causal inequality. So what we can do in this case? So this what they are saying is that they say that you start with a arbitrary causal inequality, let's say, which I have written in this form. So these alphas are positive and these are the correlations. Now what they are saying is that you can actually break a single trigger causal break a arbitrary causal inequality into single trigger causal inequalities, where each of this is a single trigger. Okay. Now what you can do is you can say that, okay, the optimal value for a general causal inequality will always be upper bounded by the optimal of each of these single trigger causal inequalities. So that's why, so the point is that if you take the particular value of zeta as zeta equal to 1, you will get some optimal value from some particular choice of instruments and some process matrix. And similarly, for zeta equal to 2, you will get the optimal from the same choice of instrument, which are the canonical instrument, but possibly a different process matrix. So the optimum for the zeta equal to 1 case and the zeta equal to 2 case might be coming from different process. So that's why this is only an upper bound. So they are not saying that this particular value will be achievable. Yeah, so that is the one of the, so yeah, so that is the last result. So there are other results also. I'm not going into that here, but so just for completeness, I will tell this. So if you do this calculation for GUI. So this was a big open question. Yeah.
Yes, yes. Okay.
Yes.
No, no. So that is what I was going to ask you, like to just briefly tell about the open questions from this paper. Yeah.
Okay. So the this was the open question, that whether we can win the GUI game or the lazy GUI game perfectly. So they have answered this question here, that lazy GUI you cannot win perfectly. And the GUI case, you can break the GUI inequality into single triggers inequality and get a bound. So the bound they derive is this one. So yeah. And then they ask that, all right, so what they have done here is we have given some geometrical characterization of the set of correlations that we can achieve via quantum processes and local instruments. So what means a trivial open question, what we can say is that, can we give further bounds, like further some principles, as in which will restrict the set of correlations that can be achieved by process metrics. So one more thing I can say is that, so this question of Cyrus-Sand bound is not solved completely, because we still don't know what is the optimal violation for general inequalities. So that is one of the open questions, like for general cases, how to get this optimal bound. Yeah. So I'll I'll think I'll stop here. So if you have any questions.
Anyone has questions? You can unmute yourself and
So
ask.
I'll ask one.
Mhm.
When you define that canonical instrument, right? So can you go back to the part where you define the canonical instrument?
Yes, 1 second. Oh, canonical instrument is where did it go?
Yeah, here.
This one,
Yeah,
yeah.
after single. Yeah. So
This
where
one
is
is
the
canonical.
definition? Yeah,
Yeah.
this one. Yeah.
This one.
So this basically says that the output is a CC state, no?
Yes. Means no, the output is a CC state only if your input is the trigger.
Yeah, only if your input is the trigger. Exactly. So now when you have this multiple, like when you go to the generalized, when it is not a single trigger thing. So in that case, like can we have some kind of generalization of this thing where output is not a CC state? Uh, did I make
Mean,
myself clear? Probably not.
means it
Maybe.
means it might happen that for general case, the optimal will not come from this kind of CC state. Is that what you mean? That
Yeah, like the optimal should come from an instrument whose output is not a CC state, right?
means should, we cannot say. Means for the general case, we cannot
Might,
say
sorry,
should, but it might.
might,
Yeah, it might. Yeah,
it
it
might.
might happen that it doesn't come from this kind. Yeah, it might happen that there is some quantum correlation in these two things. Yeah.
Yeah, so can we can we calculate the, like, anyway it will give you some kind of upper bound, no? Like that was my question. Like suppose we want to.
I understand. You are saying that. So we are saying that let's take the instrument of this particular, some other particular form. Let's say it's not a CC state, but it is some particular other form. That is
Yeah.
some, let's say, some correlated, quantum correlated state or something like that.
Yeah.
But you can do that, but how can you be sure that it will give you the optimal? You cannot be. That's why you see there was this theorem 2. So theorem 2, what was theorem 2 saying?
Mm.
that if you have arbitrary instruments for every party, it might be
Mhm.
now these instruments takes into consideration all those kind of instruments which you are also saying that it might be the output
Yeah,
is
yeah, yeah,
correlated. Some all those instruments you take. If
yeah.
your inequality is single trigger, I can always decompose that mi as convex mixtures of canonical instruments.
Okay.
So that
Uh,
means that it will always come from some canonical instrument.
so there is no need to consider other kind of instruments. You're saying the canonical
Yeah. I
instrument
mean, in the single trigger case. So
in the
here
okay.
I have written canonical instrument, but like actually it is
Oh,
little bit modification to canonical instrument, but you can see that if you are interested. I'm not
yeah.
going
So
into that much detail, but
you mean
yeah,
that only that part would change, like where instead of the CC state, it can be a quantum correlated state,
Hmm.
the output. Right. It is not technically the canonical in that sense, strictly canonical, the way you defined here.
Yeah, it's not strictly canonical, but
Uh,
okay, means if you want, I can define that also.
no,
But
I got it. It's fine. Yeah. I
yeah,
just wanted to
yeah,
see that this thing is the same as
yeah,
this one. Okay. Thanks.
yeah.
Okay,
So
so
basically, what happens is that this single trigger case is a very special kind of payoff alpha. So this alpha for the
Mhm.
single trigger case, what they make sure is that it will decompose any possible instrument to this canonical instrument kind of thing. So that's why you will always get the optimal from the canonical instrument.
For single trigger.
Yeah. For the
Yeah.
single trigger case. Yeah, exactly.
But for the general, if you say that those like all these canonical instruments are the optimal canonical instruments for those MIJs, like individual those single trigger games.
Hmm.
And like in general, that will only give you a upper bound. The optimal, whatever the instrument optimal is, it will be some kind of canon, like quote unquote canonical instrument, I would say. Just one of the
Hmm.
properties would change, like
Yeah.
something like that.
Yeah. Means like just one of them, like, so means what I meant was this that like if you have this
I guess,
MI,
Sahil,
yeah,
we can continue the conversation. Just let us give someone else to ask
yeah, sure. Yeah.
question.
Okay. Sorry.
We can be in this call later. So let's ask anyone else if
Oh,
has any other question.
I'll ask him later.
Yeah,
No. I mean,
Sahil,
fine. I mean, you can stay here and ask question. Like whoever has to leave, they can ask the question and
Yeah.
get the answer.
yeah.
Maybe.
So, Sahil, I have one question. You see, you have shown that for the GYNI case, the bound is much stricter, and which should be true, 0.74, something like that. So, I have
Hmm.
two questions. First one is, do you think any principles? I mean, I don't know. Maybe this GYNI game itself can be principle, but these are some information theoretic game. A principle should be a little bit much more information. I mean, it would be some statement like. So, do you think some statement like principles can be given for which this bound can be achieved? For example, in case of Bell-CHS's things, information causality principles gives the two-root to bound. Okay.
Hmm.
So do you think for this process matrix formalism, these bounds for IGY NI optimal, some principles can be given for which this bound can be achieved, or maybe in that case it can happen that the using that
Even better,
principles it will
even better than 0.75 you
uh,
can do. It might happen.
0.75,
Yeah.
maybe 0.70 or something like that. Then we can say, okay, some of the process
Hmm.
are unphysical according to that principles, right?
No. So no. So when you say principle, you will make sure that every process matrix and every instrument satisfies that principle, right?
No, no,
Or
no, no. Why I would?
Oh, then you are saying that there might be some process matrices which are unphysical. That's what you're.
Exactly, exactly.
Yeah,
That can also be a possibility, right?
that is a
Because
possibility. Yeah.
this is the mathematical artifact what you have discussed. All these
Mhm.
process matrix things. Now, principles can arise, and principle can exclude some processes as unphysical.
Yeah. So that part, some work is done by Bruckner.
Okay,
Uh,
what?
so that is basically they define something called as purifiability of process matrices. Like means if you have a process matrix, you should be able to purify it to some process which has some. So what is the exact meaning that I am not telling, but like means I have not read that paper also, but they define some concept like this, and they say that you should be able to purify it to some process which has a global past and global future, something like that. So there are
Got it.
some processes which don't satisfy this. For example, the OCB process,
Okay,
it will not be purifiable by this definition. So
okay. But all quantum switch type of processes satisfy
switch is
this, right?
purifiable. Switch is purifiable. Yes.
Okay, good enough. Okay, thank you. I have some other questions, but I will ask you later.
Okay.
Thank you, Sahil, for your nice talk.
Yes. Any other questions? Then we can. Okay, so I guess there are no other questions. So we will stop the recording here.